This video is the second example of how to sketch a polynomial function, and this particular polynomial function for this example is going to be a little bit more complicated, but you'll be given it both in expanded standard form, negative 2x to the 6th minus 9x to the 5th plus 15x to the 4th plus 85x cubed. Looks pretty intimidating. Minus 45x squared minus 216x plus 108. But you'll also be given it in another form, in factored form. Negative 2 parentheses. This is a little bit more compact. X plus 3 raised to the third, parentheses, x minus 1/2, x minus 2 squared. Now remember, the three features that we're going to stick with in analyzing how to sketch a polynomial are the highest order term, which governs the end behavior, the y-intercept, and the y-intercept is always going to be this last constant term in the expanded polynomial, and third, the x-intercepts. And each of the various factors is going to contribute an x-intercept. So let's begin with the end behavior. And the end behavior involves negative 2x to the 6th, the highest order term. And on the right hand end, if we made x a large but positive number, we'd see that we'd get overall as a result a negative. So that means on the right hand end of the graph, the function will be traveling downward. Now on the extreme left hand end, we'd be taking negative 2 times some negative number raised to the 6th. This also ends up being a negative number, so the left hand end behavior is also downward. Alright, moving on to this y-intercept, and we get y-intercepts by setting all of the x values in the equation equal to 0. We can see that the y-intercept is simply going to be 0,108. Pretty large y value, but we'll take care of it with the scaling in the graph. Now, last, there are going to be several x-intercepts. We can see that because corresponding to each factor, there is going to be an x-intercept. And one of the x-intercepts will occur at x equal to negative 3. Another x-intercept will occur at x equal 1/2. And a third at x equal to 2. Now, remember also that any x-intercept which relates to a factor which is a cubic factor, we in the past have called these kind of x-intercepts jukes, because it's kind of like, yes, we're going to touch the x-axis, we're going to appear as if we're going to bounce off of it, but we fake you out and we go through anyway. We're calling that a juke. Any factor which is of the variety x squared will hit the x-axis but bounce. And the third variety, if the factor is just a linear factor, x to the first, then the polynomial will not only touch the x-axis but travel through. So we have the cubic variety with a kind of a swerve to it, square variety, which is a bounce, and first power or linear variety, which is a cut through. Now let's analyze the various factors. X equals negative 3, you can see that's cubic. That's going to be the type I was referring to as a juke. X minus 1/2 with an x-intercept at 1/2 that will be just a straight cut through. And we can look at x minus 2, we see it's squared. That's the type we've been referring to as a bounce. Now let's try to put this all together and create a sketch. Now, in marking off the x-axis, we can see that we're going to need an x value of -3, since that is going to be one of the x-intercepts. We're going to need also x values of 1/2 and 2. These are the 3 x-intercepts. As well, 25, 50, 75, 100, 125. I'm marking off the y-axis in a pretty large scale, since we need a y-intercept of 108. So I'm going to mark that off, y-intercept 108. And last, the end behavior. On the extreme left-hand end, we have a downward end behavior, and on the right-hand end, also downward. Now, putting this all together, and remembering that we need to have here a juke, to have here a cut through, and here to have a bounce, we should be able to get a reasonably accurate depiction of the polynomial. So here we go. Coming upward, swerve and juke, probably goes up above that y-intercept, cuts downward through the y-intercept, goes through the cut through, comes back up to the x-axis and bounces downward. So this, although rough, is probably a fairly accurate depiction of the polynomial.